We tend to think of the sun as a static, slowly burning furnace, but main sequence stars are volatile, highly dynamic entities, and under the right conditions, they reproduce. This reproductive cycle is described by the Stellar Fission and Transmutation model, or SFT. To survive, a star must maintain a delicate balance between gravity pulling inward and internal pressure pushing outward, a state known as virial equilibrium. As a star fuses heavier elements, core opacity increases, trapping heat and causing internal pressure to spike dramatically. In this liquid drop model, pressure builds at the core. When it reaches a critical threshold, the Jacobi-Poincare bifurcation point, the star undergoes equatorial fission, ejecting a planetary mass body to restore equilibrium. Stellar parturition is a predictable outcome of a star's life cycle. It puts any nearby planetary bodies on an existential ticking clock. We can already observe the extreme magnetic complexity and volatility on the surface of our own sun. The catalyst for the next ejection event will be a state of metallicity saturation in the solar core, where heavy element buildup pushes the internal pressure past the breaking point. When that ejection occurs, the severing of the sun's magnetic fields will trigger catastrophic magnetic reconnection transients. This releases a massive, high-velocity wave of blinding radiation outward into the solar system, arriving in the form of X-ray flashes and fast radio bursts, packing roughly 10 to the 38th power ergs of energy. A pulse of that magnitude would instantly bathe the inner solar system in lethal ionizing radiation. Earth's atmosphere and magnetosphere are mathematically insufficient to block a close proximity event of this scale. The entire inner system, from Mercury to Mars, will become unviable. Surviving it requires engineering a deep space failsafe. To predict how a future ejection will impact our solar system, we have to look for forensic evidence of past events right here on Earth. If planets like Venus or Mercury were ejected sequentially by the Sun, Earth would have been caught in the gravitational crossfire. Under the chronogenetic framework, a sudden shift in local gravitational potential forces a planet to rapidly generate internal mass, a process called endogenic mass generation. This sudden expansion of the planetary radius would tear the crust apart. Rather than subduction zones where tectonic plates collide, the deepest parts of our oceans are primary expansion fractures. Look at this topological map of the Mariana Trench. The V-shaped chasm is a tectonic scar from a solar fission event. As the Sun ejected a planetary body, gravitational perturbations triggered a surge in Earth's mass. The blue arrows indicate outward tectonic plate separation. The sudden volumetric increase of the Earth's mantle physically tore the crust wide open. These massive chasms formed violently, well before displaced ocean water rushed in to fill them. These abyssal trenches serve as forensic proof of past stellar birthing violence. The physics of the SFT model have already been carved into the Earth. Finding a biological refuge requires moving outward to a safe distance. At 5.2 astronomical units, the Jupiter system provides the first crucial layer of defense. At this distance, the inverse square law naturally dilutes the intensity of lethal solar transients. But distance alone is insufficient. Jupiter's moon Europa possesses a unique structural composition, a global saltwater ocean entirely encased beneath an ice shell estimated to be 10 to 30 kilometers thick. That massive layer of ice provides a near-impenetrable barrier against extreme gamma and X-ray fluxes. In the event of a stellar thermal pulse, water's high specific heat capacity acts as the ultimate buffer. As the radiation wave hits the vacuum ice interface, it causes rapid surface ablation, but the deep ocean temperatures directly below remain completely unaffected. Europa's composition makes it the only environment in the solar system mathematically capable of absorbing a direct X-ray flash while keeping a liquid biosphere intact. While Europa offers an ideal subsurface haven, Jupiter's ambient surface radiation is lethal to human crews. Vanguard missions cannot be crewed. The entire colony must be pre-built by autonomous robotic systems. The first step is breaching the massive ice shell using a swarm of autonomous subglacial drones called cryobots. These cryobots are powered by close-cycle radioisotope thermoelectric generators, like the one seen here in cleanroom testing. They utilize a hot water jet drilling mechanism to rapidly melt through the ice column. As they descend into the dark, they unspool a fiber optic power tether, creating a physical umbilical line from the surface to the subsurface ocean. Once that connection to the ocean is established, modular autonomous underwater vehicles, or AUVs, deploy into the abyssal depths. These AUVs will mine dissolved minerals directly from the surrounding seawater and hydrothermal effluent. Using advanced 3D printing capabilities, the drones extrude a composite ice silicate metamaterial, constructing the primary pressure holes layer by layer. Establishing a deep ocean habitat at extreme pressures requires structural integrity to be fully validated before a single human arrives. In situ resource utilization via autonomous robotics is the only logistical pathway to achieve this. Once the habitat hulls are constructed, a self-sustaining colony requires massive power generation entirely disconnected from the sun. Europa's seafloor provides this energy through extreme thermodynamic gradients. The ocean sits at a steady -2 degrees Celsius, but active hydrothermal vents eject fluid exceeding 300 degrees. This temperature difference is ideal for power generation. Organic Rankine cycle turbines and solid-state thermoelectric generators will harvest the thermal gradient to power the grid. For redundancy, deep-water convection currents driven by tidal dissipation will spin high-torque hydrokinetic turbines, ensuring the colony never loses power. With infinite sunless power secured, the colony must cultivate a closed-loop food web in total darkness. This flowchart tracks the process. It starts with bacteria genetically engineered to metabolize hydrogen sulfide and methane from the vents. Fungi break down waste organic matter to produce bioplastics, while massive LED-lit hydroponic bays cultivate genetically modified macroalgae to scrub carbon dioxide and generate oxygen. By tapping into planetary heat and deep-sea kinetic energy, an artificial closed-loop biosphere can sustain a human population indefinitely, regardless of what happens topside. There is one major engineering hurdle remaining. At a depth of 100 kilometers, Europa's seafloor exerts a crushing hydrostatic pressure of 131 megapascals. That is equivalent to the deepest point of Earth's Mariana Trench. Building massive, cavernous civilian habitats at those pressures severely limits usable internal volume. The solution is the bathypelagic suspension model. Instead of building on the seafloor, the primary civilian habitats are anchored directly to the underside of the massive ice shell. Up at the ice ceiling, the pressure drops to a much more manageable 10 to 20 megapascals. High-pressure umbilical elevators connect these suspended ceiling cities to the automated mining and power facilities down on the vent floor. Physically decoupling the population centers from the extreme pressures of the geothermal power sources unlocks the volume necessary to house a viable civilization. The stellar fission and transmutation threat is an inevitable secular instability. Because we cannot predict the exact moment of the sun's parturition, deploying this failsafe requires a strict, accelerated schedule. The first 3 years are dedicated to terrestrial analog testing in deep ocean trenches, followed immediately by the launch of the cryobot Vanguard to penetrate the Europan ice. In year 8, the AUV swarm arrives. As shown in these central panels, they begin automated manufacturing, printing habitat holes in the dark. By year 15, the biosphere is seeded. After year 20, the human population makes the transit. The tectonic scars mapping the bottom of the Mariana Trench are a permanent reminder of planetary volatility. They show us exactly what happens to a solar system when a volatile star violently rebalances itself. Recognizing the reality of stellar parturition transforms the colonization of Europa's abyssal ocean into the single mathematical prerequisite for the continuation of terrestrial biology.